In exercise 4 of chapter 13, we will meet Robinson Crusoe, who will show us the benefits of trade. So, Robinson Crusoe lives on an island, he produces and consumes fish and coconuts, and he has 2 hours of work available to work. And he doesn't really mind whether he is catching fish or coconuts. He likes it equally well, or dislikes it equally well. So he's indifferent between the two. But he does have a production function, and his production function for fish is like this. So the number of fish that he catches is the square root of the number of hours that he puts in. And the same for coconuts. And in total, he has 200 hours to spend. So his constraint is that the total number of hours cannot exceed that number. And his utility from consuming fish and coconuts is a very standard Cobb-Douglas function. So he likes to have both some fish and some coconuts to consume. And then the question asks a couple of things. So first, in question A, we have a situation where Robinson cannot trade with the rest of the world. How will he then allocate his labor? What will he produce? And what will he then consume? Well, in this case, given that he cannot trade, the coconuts and the fish that he produces are the same as what he will consume. What will then be his utility, and what will be the rate of product transformation? That's question A. Then in question B, we lift a constraint for Robinson, so we allow him to trade fish and coconuts with the rest of the world at a price ratio equal to 2 to 1. But we impose that he produces the same fish and coconuts as in question A. And then in question C, we lift another constraint, so we also allow Robinson to adjust his production of coconuts and fish compared to the levels in question A and B. So it's even more flexible here. And what you will see is that if we move from question A to B to C, the utility of Robinson will increase. So trade turns out to be beneficial to him. And then question D, we are asked to graph the results of the preceding questions, but we will do this on the fly. Okay, we start with question A. And I repeat here the production functions and the constraint and the utility function. And in question A, we're in a situation of autarky. So what we first need to do is to determine the production possibilities frontier, given that he has 200 hours to spend, which combinations of production of fish and coconut are available to Robinson. And note that if we take the squares of the production function, then we get the following expressions. And this comes in handy because we can plug this into our constraint of the 200 hours. So the production possibilities frontier is of the form f squared plus c squared needs to be equal to 200, which we can rewrite as a constraint, namely that whatever f and c we choose, this constraint needs to be satisfied. So for example, if we would want to have 10 coconuts, so then c squared would be 100, then we could also produce 10 fish, because 10 squared plus 10 squared minus 200 satisfies the constraint. So the point 10, 10 is 1 point of the production possibilities frontier. So, and together this is the relation that gives us the entire frontier. And then we need to compute the slope of the frontier. So we can rewrite this frontier as a function of f. So the production of coconuts follows from our choice of the production of fish. It's actually the number of time that is remaining to produce coconuts. We can take the squares of the left hand side and the right hand side, get the following expression. And then we can take the derivative of this thing with respect to f, which amounts to 1/2, and then the derivative of the thing within parentheses, which is minus 2f, and then the original part within the parentheses, and then we reduce the power here by 1. And then if you simplify this a little bit by replacing the 200 minus f squared by this expression over here, so we can just replace it by the consumption level, we get that the slope of the production possibilities frontier is the negative of the ratio of fish and coconuts. Other way to do it is to use the total differential to find the slope. So this is the negative of the rate of product transformation. So we are tied to spending 200 hours. That determines our PPF. So we need to, if we change the production of coconuts, then we also need to adjust downward the production of fish in order to remain on the same frontier. So the total differential has the following form. We can take the derivative of this expression with respect to c, so that's equal to 2 times c. The derivative with respect to f is equal to 2 times f, and we get this expression, and then we solve for delta c over df, and we get the same expression as what we have here. So this is the rate of product transformation, which then is also the rate of product transformation is the negative of the slope of the production possibilities frontier. So there are two ways to do it. So one, use the total differential to find the slope. Other way is to rewrite the production of one good as a function of the production in the other good and take the derivative in order to arrive at this slope. Okay, so check, we have the RPT. We don't have the utility, but we will get to that. And notice that this is similar to equation 2.40 in the book, which is from the math chapter. The math chapter tells you how to deal with the total differential, and here I translated what has been stated there to the context that we consider now, plugging in the C and the F's. Okay, so Robinson will choose the production of fish and coconuts such that he reaches maximal utility, and the point where his utility is maximal is where the rate of product transformation is equal to the marginal rate of substitution. So the RPT is about what he's able to produce given his production functions and his number of hours, and the marginal rate of substitution is derived from his preferences. And this point is the point where the rate of product transformation, where the production possibilities frontier is tangent to the highest indifference curve that he can reach. Okay, so the marginal rate of substitution is the marginal utility of fish divided by the marginal utility of coconuts. We have a simple Cobb-Douglas utility function, and solving this we get that the marginal rate of substitution is equal to C over F. Now we're in the position to equate the two, and doing so gives us that F over C should equal C over F. So bringing the F to the left hand side and the C to the right hand side, we get that S squared is equal to C squared. So in equilibrium, our consumption and production of coconuts needs to equal the production and consumption of fish. But then, final question, what is the amount of consumption of coconuts and fish? Well, we plug this value into our original constraint. So we replace the F squared over here with the C, giving us an equation in one unknown, consumption of coconuts. We arrive at 2 times c squared is equal to 200. So the production and consumption of coconuts is equal to 10, giving us a utility of 10, and the rate of product transformation at this optimal point is equal to 1. And that's complete question A. And you can also see this graphically. So graphically, the production possibilities frontier is this curve that we have over here. So at this point, we only produce fish. At this point, we only produce coconuts. One option is to catch 10 fish and to gather 10 coconuts, which is the point over here. And this also happens to be our equilibrium solution in Arctic, because this is the point where the indifference curve associated with a utility of 10 is tangent to the slope of the ppf, being the rate, the negative of the rate of product transformation. So this is the solution to question A. Okay, then we are ready to do question B. And in question B, trade is opened and Robinson can trade fish for coconuts at a price ratio 2:1, so that the given world price, he cannot influence it. And he needs to continue the production of coconuts and fish at the same level as in part A. So what happens here is Robinson still produces coconuts and fish equal to the amount of 10, but he is not necessarily bound to also consume 10 fish and coconuts because he is now able to trade some of the fish or coconuts with the rest of the world at a given price ratio of 2:1. And that means that he can move away from this initial point over here by trading in some fish for additional coconuts. So every fish that he sells gives him the opportunity to buy 2 additional coconuts. So we have a line here with the slope being equal to the negative of the price ratio of 2. And Robinson can now trade and move along this line. And as you can see in this graph, and we will get there also by doing the derivations, this allows him to reach a higher indifference curve. And the new optimal consumption bundle is the point where the indifference curve is tangent to his budget line. So this is kind of a budget line. And in equilibrium, he will produce still 10 fish and 10 coconuts, but he will consume less fish and more coconuts. So he will consume 7.5 fish and 15 coconuts because that gives him a high utility. So he trades some of the fish, 2.5 fish, for 5 additional coconuts. Okay, so this is what we aim to do. This is the final outcome, and now I will guide you through the derivations. So production is not adjusted, but trade is possible, and at the optimum consumption bundle, Robinson will choose the point where the marginal rate of substitution is identical to the price ratio, 2:1. So to solve for his optimal consumption, we plug in the marginal rate of substitution. From the previous exercise, we know that this is C over F. And I added an index C here to consumption and to coconuts and fish to distinguish between the number of coconuts and fish that Robinson produces and the number that he consumes. So in the end, he will consume twice as many coconuts than he will consume fish. And we know that the optimal consumption bundle is somewhere on this optimal budget line, and the budget constraint is given by what he produces. So that determines his earnings, and his total budget is the number of coconuts that he gathers times the price that he receives for a coconut, and the number of fish that he catches times the price on the world market for fish. That together determines his income. So he continues to produce 10 of each. So his income is 30. And then having an income of 30, he can freely spend it on either coconuts or fish by trading. So his budget constraint for consumption is identical to 30 is equal the number of coconuts times the price of a coconut plus the number of fish times the price of a fish. And now we can substitute the number of coconuts as a function of the number of fish into this expression, replacing the CC over here. Again, we get one equation with one unknown. We solve for the consumption of fish, and we get that in equilibrium, Robinson will consume 7.5 fish and 15 coconuts. And its total utility will increase from 10 to about 10.61. So Robinson benefits from trade. But is that all? No, that isn't all, because Robinson can do even better. So what Robinson realizes is that the price of fish is relatively attractive, and the world likes fish more than he likes fish to some extent. So he can benefit from also shifting his production, because now trade is possible. He can produce some more fish for the market and sell it to other people. So in question C, Robinson is allowed also to adjust his production. And what we will observe is that, realizing the quite favorable world prices for fish, he will decide to produce more fish and less coconuts, and then by trading some fish on the world market in order to buy more coconuts, because he has a comparative advantage in catching fish. So what we will see in question C is if he is able to change the production, he will choose the point of the production possibilities frontier where the slope of the PPF is identical to the world price ratio. So he will choose the point over here. And then subsequently he will trade in some fish for coconuts in order to find an optimal consumption. And the optimal consumption bundle, again, is the point where the marginal rate of substitution is identical to the price ratio. And that will get us at the point here. And as you can see, in this new equilibrium, the Robinson is able to reach an even higher indifference curve than in question B. So this is what we are going to do in question C. So this is question B. So we move from this point to this point over here. And in question C, we will show that when Robertson can change his production, he is able to move even from this point to this point over here. Okay, so Robinson can now both trade and adjust production. At the optimum consumption, it still needs to hold that the marginal rate of substitution is identical to the price ratio. So he will still consume coconuts and fish in a ratio 2:1. But now his new production is chosen such that the rate of product transformation, so the slope of the PPF, is also identical to the price ratio on the world market. So in his new production levels, he will also produce twice as many fish as coconuts. So what will then be the total amount of coconuts and fish that he will produce? Well, he produces twice as many fish as coconuts. We plug this into the expression. In total, he still has 200 hours to spend. So in the new equilibrium, he will produce the square root of 40 in coconuts, twice that amount in fish. And we can simplify this a little bit. So this is the production, which also determines Robinson's new budget. And because of the favorable prices for fish, his new budget is bigger than the budget that he had before. So we can plug this in. The price of coconuts times the number produced plus the price of fish times the number of fish produced, and his new budget is 5 times the square root of 40. He consumes coconuts and fish in the ratio 2 to 1. So we plug that into our new budget of 5 times the square root of 40. And we get that replacing the CC over here by 2FC, we get that 4 times FC is equal to 5 times the square root of 40. We can solve for FC and we get that in the new equilibrium he will consume 2.5 times the square root of 10 of fish and 5 times the square root of 10 of coconuts. And this is exactly this point over here. And its total utility, plugging these numbers into the utility function, we arrive at a utility of 11.18, which is again higher than the utility in question B. So the benefits of trade and the opportunity to adjust your production is even higher than calculated in question B. And then exercise D asks us to graph the results for A, B, and C, but as promised, we already did it on the fly. So this completes exercise 13.4.